Hello there, everybody. My name is Professor Ian Jones. I work here in the Gravity Group in Mathematical Sciences in the University of Southampton, and I'd like to offer you a very warm welcome indeed to this, which is the first live on YouTube and Facebook broadcast of the 2022 Southampton Science and Engineering Festival. So this festival starts today and it runs on until the 20th of March. And I'd very strongly encourage you to take a look at some of the other things that will be happening over the next week and a half or so. My talk, as you're about to hear, is basically on the astrophysics side, but we've got all sorts of exciting things coming up. We've got other talks related to astrophysics, geometry, sustainability. There's even one related to Jurassic Park, climate change. There's all sorts of interesting things coming up, and I very much hope that you'll get a chance to check some of them out. And there's a hashtag SOTSEF if you want to communicate any of this to any of your friends. So let me make a start then. So my talk is going to be about gravitational wave astronomy. As we go along, you're very welcome to put any questions that you might have in the comments box. I'll probably wait until the end before answering them, but we'll see. So gravitational wave astronomy, subtitle, A New Window on the Universe. What on earth is this all about? Well, if we move on to the next slide, what you can see here, two funny looking squiggles, which created an awful lot of excitement at the time. Let me say a little bit about what they are, but really explaining the significance of this is the main thing I'm trying to get at today. These, if you look carefully at this little picture, there are two rather jagged, random looking signals on it. And these are the outputs of two so-called gravitational wave detectors. What we're seeing here is a signal that we detected back in September 2015 that basically represent little wiggles, little waves in the gravitational field. The reason that there are two wiggles here is that, in fact, there were two gravitational wave detectors operational then. They were both in the United States, widely separated, one at the top northwest of the country, one in the southeast. And they both picked up this signal, which you can see sort of starts off weak and gets stronger as time went by. So that was detected in September. There then followed about 6 months of very hectic work. Then in February of 2016, we announced to the world just what we'd seen. And our claim was that we'd seen gravitational waves, these ripples in the gravitational field, from two colliding black holes. Now, I say this was big news at the time, and I'm not exaggerating. If we go on to the next slide, this is the front page of the Independent newspaper that came out immediately afterwards. So you can see they've devoted the whole of the front page to this story. There's a certain amount of artistic license in that picture there. The idea is that it's an image of two black holes with some stars behind them, and the light from the stars is getting distorted. But no one took this image. This is sort of, a somewhat informed artist's impression. Rather naughtily, the headline is "The Theory of Relativity Proved." Now, you may realize this, but sadly, in science, we're never actually in the business of proving anything. And you might find that sounds a bit odd, but really, when we have a theory, we can disprove it by showing that it doesn't agree with nature. But what the headline should have been was something like "Prediction of Einstein's Theory Verified." But of course, we never quite prove theories. That was the Independent. If we move on, this was the front page of the Telegraph. So for those of you that can't remember or are too young to remember, this is what a newspaper front page looked like I used to say the days before Brexit. Then I could say the days before COVID, and I guess now the days before Ukraine. But this was the front page of the Telegraph, and you can see it's got a big and very fanciful picture of something to do with black holes on the front. But again, a big story there. And this next one on the next page is a bit of fun. This story even made it onto the front page of the big issue as well. And no, that's not a real astronaut. So if we move on, the questions I'm going to try and answer now are: what are gravitational waves? So the detectors that actually saw these things were the LIGO detectors. So why were these LIGO detections such a big deal? Those are the two questions I'm going to try and answer today. So this story actually goes back a very long way indeed. So if we move on, in fact, it goes back all the way to 1915. So obviously there's a picture of Einstein there. In 1915, Einstein published his theory of general relativity. Basically, you can think of this as his theory of gravity. It's a rather, in some ways, mysterious theory. Einstein taught us to think of gravity not as a force, but as a curvature in space-time. And you can see there's a little picture of sort of a rubber sheet geometry there of like a big gravitating mass, something like the sun, and something following a curved path around it. This rather abstract idea of curvature in space-time, we don't really need for the story I'm going to tell you today. What's more important is this remark that I've put at the bottom of the slide. So one of the principles on which Einstein based his theory of general relativity was the idea that nothing can travel faster than light. And in fact, later today, my colleague Sunny is going to give a talk specifically on Einstein's special, not general, but special theory of relativity that deals precisely with this point. But the takeaway here is Einstein put this idea that nothing can travel faster than light into his theory of gravity. And that had some profound implications. So if we move on, the first of these profound implications was realized just 1 year later in 1916 by Schwarzschild, who, despite Einstein's theory looking really messy and complicated, managed to find a rather elegant and simple looking solution to it. Nobody used this name at the time, but it's what we now call a black hole. So the idea with a black hole is that if you have got such a strong gravitational field, so if you take like a star and you shrink it and you shrink it and you shrink it, so that the gravity is getting stronger and stronger at its surface, eventually it'll reach the point where the escape velocity of something at the surface, so how fast you'd need to throw something for it to escape the star, would exceed the speed of light. But Einstein taught us that nothing can go faster than light. So this really is what leads to the idea of a black hole, the fact that you can have strong gravity and that things can't travel faster than the speed of light. And the images that you can see on this slide, well, if we start on the left, again, I realize this is an artist's impression. We don't see things like this in this much detail. This is what we think is going on with a particular black hole called Cygnus X1. The black hole is on the left of this picture, and there's a big star, big sort of normal star on the right. And what's happening is the black hole is ripping off some of the gas from that normal star, and that gas is forming a disk and swirling down onto the surface of the black hole. And just as, say, when you pump up a bicycle tire and you're compressing gas a lot, it heats up. So this gas that's falling into the black hole, it's getting compressed, it's heating up, and in fact, it gets so hot that it starts emitting not normal optical light, it starts emitting X-rays, so very, very high energy light or high frequency light. So the image that you can see on the right, it's got a little, well, it's got a few things labeled, but one of them is Cygnus X1. This was something that was discovered by X-ray astronomers many, many years ago, and it was basically our first candidate black hole. So we can't really see the black hole itself, and in a sense, you never can, right? But we could see the presence of the black hole because we could see the gas falling in, and it was basically producing a sharp point of light, or X-ray light at least, that astronomers could see. So let's move on to the next slide. So that was the first implication of this universal speed limit in Einstein's theory of gravity. But there's another, and in fact, this was an idea that Einstein himself came up with just 1 year after he published his theory, so in 1916. And what Einstein did was he thought about the problem of changing gravitational fields. So whenever things move around, the gravitational field they produce changes. But Einstein's theory had this idea that nothing could travel faster than the speed of light. And what Einstein realized was that this speed limit applies to gravity itself. So what you can see, and again, this is a slightly fanciful picture here, are two stars in orbit around one another. So they're big, massive objects. They're moving quite fast. And because they're moving around, the gravitational field that they produce changes, and that change propagates out at the speed of light. And it's precisely this. This is what we mean by a gravitational wave. It's a little change, well, in this case, it could be a bigger change in the gravitational field that's produced as bodies move around. So that's it. The bottom line says it all. These ripples in space-time are the gravitational waves. So next slide, please. So the question then becomes, what produces these gravitational waves? Well, the answer to that is pretty much everything. So I'm sitting here in this chair, and if I move my arms around in some way, I'm moving some mass around. That in itself produces a gravitational field that changes in time. But, and you can put the numbers into Einstein's theory and work it out, the strength of those waves is very, very small. They're very, very weak. What you need in order to produce strong gravitational waves are very massive objects moving at high speed. And by high speed, I mean speeds as close as possible to the speed of light. And so when you study this in detail and put the numbers into Einstein's theory, what you quickly realize is that there's not much hope of like us generating detectable waves gravitational here on Earth. What we need to do is we need to look out elsewhere in the universe, in the world of astronomy and astrophysics, where you do get big masses, heavy objects, where you do get things moving fast to produce strong gravitational waves. And that's precisely what this slide is showing. What we often do is we categorize different sorts of sources of gravitational waves into these four classes here. So the top left is the thing I've more or less mentioned already. If you've got two stars in orbit around one another, well, that will naturally give you big heavy masses moving quite fast. So that will produce gravitational waves. But that's not the only thing. Top right, exploding stars. What do I mean by that? Well, you probably all heard of supernovae, right? It turns out that when normal stars reach the end of their lives, they start burning their nuclear fuel more and more quickly, and the process gets out of hand. And what happens is you get a supernova explosion, and you get one of these very pretty massive clouds of plasma, basically, that you can see in that top right picture there. That, in fact, is a picture of a very famous nebula called the Crab Nebula. In fact, we think that Chinese astronomers even saw this star explode by seeing a new star appear briefly in the sky back in the year 1054. So we can date that one quite nicely. But the point is, an exploding star will have lots of matter moving around very fast, and that can produce some strong gravitational waves. Bottom left, another thing that we're interested in is detecting gravitational waves that aren't as violent. They don't involve two stars. So in the top left picture, those two stars, they're orbiting around one another, but the gravitational waves are only strong when the two stars are close to one another. And when they're close to one another, they're emitting a lot of energy in gravitational waves, and that energy has to come from somewhere, and it comes from the energy of the orbit. So as these two stars orbit around one another, if I do it like that, they gradually get closer and closer, and they eventually coalesce and form one star. So it's a violent event. Similarly, these exploding stars are violent events, short, sharp bursts of gravitational waves. The thing on the bottom left that we're also interested in are much gentler events. Stars in general rotate. There are some stars that we know of in our galaxy that are very small and dense and rotate very fast. These are called neutron stars. They're called that basically because they're mainly built out of a fluid made of neutrons. They're basically what you can get left behind when a normal star dies and collapses, and the core collapses, and it can leave behind a neutron star. And in fact, to make contact with that exploding star picture on the top right, we think that when that star in the Crab Nebula exploded, its core collapsed and it formed a neutron star that we see today. And we see that star is spinning around really steadily at about 30 times a second. So it's spinning very, very fast. If there's some little sort of bump on that star, so it isn't perfectly rotationally symmetric about its spin axis. We say that, if there's a mountain on it, but we don't really mean a little pimple. We mean some sort of it's just sort of elongated, more like a rugby ball, say. If there's some sort of if it's not rotationally symmetric, as it rotates, its gravitational field will vary in time, and that motion will emit gravitational waves. And that sort of signal, in contrast to the short-lived, things of order seconds from the top two pictures, that could last millions and millions of years. So it's a signal that, in a sense, would be there all the time. And finally, the fourth class of gravitational wave source, and in a sense the one that we'd be most interested in seeing, is gravitational waves from the Big Bang. You may well recognize that picture bottom right there. This is a picture of not gravitational waves, but electromagnetic waves, so basically light that was left over after the Big Bang. So this is one of the most famous pictures in astrophysics. It's the so-called cosmic microwave background. So this is some radiation that we think, some electromagnetic radiation, so some light that was produced very early in the universe, when the universe was about 380,000 years old. And the universe was very hot at the time, but the universe has since expanded and cooled down. And we actually see that light now in the microwave part of the spectrum. So we can't see it with our eyes because it's cooled so much. It's got lower frequency than the optical, but we can detect it. And that's some radiation, some electromagnetic radiation left over after the Big Bang. And people have done an awful lot of interesting cosmology work with that. So you can see it's colored, right? Some bits are red, some bits are blue. What that color coding is showing is that the microwave background is hotter, slightly hotter, not much, but slightly hotter in some directions than other. And that's telling us something about how much structure there was in the early universe. And by early, we're talking, as I say, about 380,000 years. What we would love to see is the gravitational wave analog of that. In other words, some sort of random gravitational wave background coming from all directions in the sky. And if we were to see that, then we'd be getting a snapshot of the universe, not when it was about 380,000 years old, but rather when it was just some fraction of a second old, because gravitational waves interact much less strongly with matter, so they don't get corrupted as the universe evolves. So they give you sort of more pristine information about what the universe was like when it was very young. So that's the so-called stochastic background, which we've not seen, but we'd love to see. And in terms of what we've actually seen so far, well, I'm going to tell you about this in more detail, but so far we've only seen events from the top left. We've only seen binary stars colliding. We've not seen exploding stars with gravitational waves. We've not seen spinning neutron stars, and we've not seen anything left over from the Big Bang. We're looking, but so far we've only seen these so-called colliding compact stars. We call them compact because the stars have to be small and dense for this to work. So they need to be either black holes that I've mentioned or neutron stars. Let's move on to the next slide. So there was a lot of interest in trying to detect gravitational waves, but before you do too much in an experiment, you want to make sure that you're looking for something that's real. And in fact, there's a very interesting historical story here. So I told you that Einstein, all the way back in 1916, did a calculation that showed that changes in gravity move out or move around as gravitational waves. Actually, the story is a little more complicated than that, because Einstein lost faith in that calculation, and for a while at least decided that gravitational waves might not be real and that they were just sort of a trick of the maths and they don't really correspond to anything. And as extraordinary as it might seem, this debate raged for several decades until in the late 1950s, people that looked very carefully at the theory of general relativity produced some fairly robust arguments that they were real. So those convinced most people. But then what took the story to the next level was what I would call an indirect detection from many years ago now of gravitational waves. So what is going on in this plot here is as follows. So this story is about a pair of stars in orbit around one another. So it's one of these binary systems again. the two stars, they're both neutron stars, so these small dense stars. Um, these two stars are quite close, but not very close. So they're close enough that they are emitting some significant gravitational waves. So they're losing energy, and their orbit is shrinking as a consequence, because that's where the energy comes from the orbital energy. And what this plot is showing are taking some measurements that were taken painstakingly by astronomers, by radio astronomers, in fact, all the way from the 1970s. This plot goes up to the year 2005, but it's been extended since, but this is a really beautiful version of it. And what they saw was that the orbit of these two stars was shrinking. So these little black dots that you can see are basically data points giving information about the size of the orbit as time goes by from year to year. And that black curve that you can see that goes nicely through those dots, that's Einstein's prediction. That's the general relativity theory prediction of how the orbit should shrink if it were emitting gravitational waves as predicted by Einstein's theory. And you can see the agreement is excellent. And indeed, this one, Halson Taylor, so two of the astronomers that were pivotal in getting this data and interpreting it, it won them the 1993 Nobel Prize. So that was a big deal, and it added to our confidence that gravitational waves were real. But nevertheless, it wasn't really what I would call a direct detection. We'd seen the effect of the waves on some distant bodies, but we hadn't detected them. So the question then becomes, can we actually detect these little ripples in the gravitational field? So let's go to the next slide. So this shows an experiment from the 1960s by a pioneer in this field called Joseph Weber. And so by this point, people had convinced themselves that gravitational waves were real things. And what they'd realized was that gravitational waves really do have an effect on anything that they propagate through. So if I can just put my hands up, if these are two like little objects floating in space, if a gravitational wave comes along, what it tends to do is exert a little force on them and make them shake in and out. So it's what we might call an oscillatory force. So it tends to make objects oscillate or vibrate. That's the effect of a gravitational wave. And so Joseph Weber understood this. And so you can see a picture of him in his laboratory with one of these early gravitational wave detectors. And basically, it's a huge, that's to say, meter-long bar of aluminium. It's called a bar detector for that reason. And the way it works is this. So Weber went to great pains to isolate this bar from all the seismic noise and other random vibrations that could be affecting his laboratory. And he thought he'd done a pretty good job, such that when he did occasionally see this bar oscillate in some way, he'd say, a gravitational wave has just passed through. And he claimed to be seeing fairly regularly gravitational waves. So that was a huge deal at the time. And other research groups around the world very rapidly tried to replicate his results. But then the story goes a bit wonky. Basically, nobody could duplicate his results. And when you actually did some calculations and figured out how plausible it was that exploding stars or colliding stars could be producing this amount of gravitational wave energy, the numbers didn't work out. Basically, all the energy in the galaxy would sort of, have dissolved away long ago if gravitational wave energy was being produced as rapidly as he was. So in fact, even though he really was a genuine pioneer, we're sure he really didn't make genuine detections. Until the day he died, he was convinced that he did. But the consensus now is that he didn't. And one of the reasons was we think that his experiment was quite small. And it turns out it's easier to detect gravitational waves if you can build a really, really big detector. But the trouble is, it's difficult to build a huge, really, really long bar. Let me step back a second. So the idea here is that if Weber could have built a bar that was twice as long, the effect that he was looking for from the gravitational waves would have been twice as big. And if it was 3 times as big, the effect would be 3 times as big. But of course, there were just practical limitations. So what people realized in the 90s was there's a better way of doing this. So if you go to the next slide, and in fact, this is actually an animation. So could we start playing it, please? So what people realize, there's a different way of looking when objects are set in oscillations. The idea here is we've got a laser. Its light is being split into two halves. One half of the light, so here's the light, it's hitting the mirror, it's split into two halves. One half goes along one arm of this L-shaped detector, and it bounces off this mirror at the end, and then travels back. Meanwhile, the other half of the light went up the other half of the arm, and then those two beams recombine, and you can see that they're being projected onto this little screen on the right. And what's going on here is that we've got two laser beams. They've traveled along different paths, and they're being recombined. And you probably know that when waves combine, you can get interference. You can get positive interference where the peaks overlap and the troughs overlap, or you can get destructive interference. And that's what you can see. We're going from constructive, destructive, constructive, destructive. What this is doing is giving us information about any changes in length of these two arms. And what we think is a signature of gravitational waves is that when one of these two arms is a bit shorter than normal, the other's a bit longer. And that is precisely the thing that this changing interference pattern can show up. And so if we go on to the next slide, this is an aerial view of how this was actually put into practice. So this is one of the two American LIGO detectors. LIGO is an acronym. It stands for Laser Interferometer Gravitational Wave Observatory. That animation I just showed you, that is a laser interferometer. Interferometry just basically means taking two sets of waves and combining them and seeing how they interfere. You can see there's a little building at the bottom right. So that's the so-called corner station. So the laser is in there. There's a James Bond like control room with loads of fancy charts and figures and so on. And stretching off into the distance, that's one of the two arms that make up this L shape. The other arm is going off to the left. That is 4 kilometers long. In other words, this experiment is 4,000 times bigger than Weber's experiment. And so in that sense, it's 4,000 times easier to pick up the signal that we're looking for. These gravitational effects are what we call tidal. As I said, if you make your experiment twice as big, the stretching that you get as the gravitational wave comes through is twice as big. So if you make your detector 4,000 times bigger, the effect you're looking for is 4,000 times bigger. So that's why LIGO was built with such incredibly long arms. It was still a very, very difficult thing to do. These arms are actually vacuum tubes, because if there was air in them, they would completely contaminate and mask the signal that you're looking for. All the parts of the apparatus that have got anything to do with the laser being bouncing up and down are suspended on multiple pendula so that they don't shake around too much. Basically, it pushed all components of its technology. So the laser powered the vacuum tubes, the Isomix isolation to its limit. This experiment is sensitive to length changes in those arms of a few times 10 to the minus 15 meters. If you're not familiar with that sort of notation, what that means is it's 1 divided by, and then 1 with 15 zeros meters. So it's a fraction of the size of an atomic nucleus. This is why detecting gravitational waves is difficult, and this is why it took a long time. The size of the effect that you're looking for, even with a huge experiment like the LIGO experiment, is very, very small indeed. Can we go to the next slide? So this is bringing the story more up to date now. So back in September 2015, the LIGO experiments were operating. They'd actually been operating since about the year 2004, taking data, gradually getting better and better data, but not detecting anything. And it was an endeavor that cost millions, actually hundreds of millions of dollars or pounds or whatever unit you like. It was a big venture, but at that point, after having taken data, well, the first data taking was 11 years ago, it still hadn't seen anything, and so we were, hoping against hope we would, and gradually improving the data. What actually happened was that after we'd taken data for about 8 years or so, the detectors then, as was planned, were shut down for a while and greatly improved, and they came back in the so-called advanced configurations. And almost immediately, when they were switched back on again, this happened. So these are slightly more scientific versions of that plot that I showed you at the very, very beginning of my talk. The top plot is the output of the LIGO Hanford detector. So Hanford is in, so this is the name of one of the two LIGO detectors. It's in Washington State. So that's at the top northwestern corner of the United States. This was the signal that was seen in the Hanford detector. And then at almost exactly the same time, the signal that you can see in blue was showed up in the LIGO Livingston detector. So Livingston is in Louisiana. It's at the very southeast of the United States. And there was a small time delay between these two detections of order of a millisecond. And that made sense because that was the time it would take the gravitational wave to propagate from one place to the other, given that it was traveling at the speed of light. And the very bottom plot here shifts by this fraction of a millisecond to line the signals up. And what you can see is that, so on the horizontal axis, it's time. The vertical axis is basically the output of the detector. The absolute units don't matter. You can think of it as a measure of the length change in the arms of the detector. And you can see that at early times, actually, the signal is really weak, right? And you can't quite see it by eye. But as time goes by, there's some sort of signal that you can then pick out by eye. It's getting bigger in amplitude. And in fact, you can just about see its frequencies increasing. And then at a time of about 0.42, 0.43 on this plot, it then ramps down again and eventually disappears. So the whole thing was there for about half a second or so. But the point was it showed up in both detectors. It was quite noticeable. It was quite strong. And this, it was claimed, was the first detection of gravitational waves. And the key point is this. People had, by this point, done calculations as to what would happen if you've got two black holes in one of these binary orbits and that they emit gravitational waves and they shrink all the way to the point of colliding, or coalescing is what we say, and forming a single black hole. And basically, this signal that you can see there that starts off with low amplitude and low frequency, the amplitude and frequency then increase to some maximum and then rapidly shut off. This is precisely what Einstein's theory of relativity predicts for gravitational wave emission from this compact binary black hole coalescence. So that was the defining moment in the field. If we go to the next slide, so that was detected back in September 2015. There was then a frantic 6 months of analyzing this, and we had to convince ourselves that this truly was a real event, because of course in any sort of experimental science, occasionally just random noise can happen to look like the thing that you're looking for. So you've got to understand the noise in your detector as well and do statistical analysis. But anyway, we eventually, quite rapidly convinced ourselves it was real. And so then in February 2016, published this paper. I don't normally show abstracts in outreach talks, but there are a few almost amusing things to pick out here. Let me just pick out a few of them. One of the things that it says here is that the gravitational wave. Sorry. Let me step back a second. So look at the author. The author is P.B. Abbott. I'm sure you can guess what's going on here. The authors are listed alphabetically, and Abbott was the first in alphabetical order: A, B, B. Now, at some point in the collaboration, there was actually someone called a baddie whose surname began ABA, and at another point, there was someone called Arsi, AASI. it gives you some idea. This was a big project. There are about 1,000 authors on that paper because there's people that do the experiment, there's people that do the data analysis, and there's people that do the calculations, modeling sources. So it's a big endeavor. But anyway, let's just show you that it was a big team effort to get this. Let me just pick out a few numbers from this, the abstract, the summary of the scientific paper. It says that the gravitational wave strain was 10 to the minus 21. What on earth does that mean? What it's saying is that the fractional length change of the two arms in our detector, so how much they went in and out as the gravitational wave came through, was 1 part in 10 to the 21. So 1 divided by, then 1 with 21 zeros. That's how weak, that's how small the effect of this gravitational wave was. That's why it was such a difficult thing to detect. But it did match the signal Einstein's theory predicted. It did show up in both detectors, and we were eventually able to convince ourselves that it almost certainly was a genuine signal, because the chances of it being a spurious, just noisy event was something like that would happen just by random chance, only once in about 200,000 years. So, it was a very confident detection. In terms of distance, it was order a few hundred megaparsecs away, which is of order hundreds of millions of light years away. So it's in a far distant galaxy. These things occur so infrequently, we wouldn't expect to see them anytime soon in our own galaxy. And here's a funny thing. So the masses of the two individual black holes that made up this binary system, one had 36 times the mass of our sun. The other had 29 times the mass of our sun. We predict that they coalesced, they formed a single black hole, and that final black hole had a mass of 62 times the mass of our sun. Now, if you do a bit of mental arithmetic, you can see that there's a shortfall here. 36 plus 29 is 65. There's a shortfall of 3 solar masses, and it's not because there's anything wrong. That's how much energy, if you think in terms of Einstein's famous formula, E equals mc squared, the equivalent of 3 times the mass of our sun was converted into energy, gravitational wave energy, in that half a second or so. So even though this signal was incredibly weak when it reached our detectors, it corresponded to the most enormously violent event, with the entire 3 times the mass of our sun, the equivalent of that, being converted into gravitational wave energy in half a second. So it was very, very violent. All right, so let's move on to the next slide. Sorry. So why was this a big deal? Well, there are 2 things to say. First of all, it was our first ever direct detection of gravitational waves. So Einstein had predicted these things back in 1916. It's the first time that we actually detected them ourselves with a machine that we'd built. It was also the first ever strong field test of general relativity. What do I mean by that? Well, people had been testing general relativity with experiments for many decades, but those tests generally were solar system tests, thing on the Earth or in satellites around the Earth, where gravity is quite weak. What we saw with our gravitational wave detectors was 2 black holes colliding and forming a single black hole. And so that's as strong as gravity can get. You can't get stronger gravity than a black hole. So whereas before we tested very, very weak gravitational fields, this is really putting Einstein's theory through its paces, because it's probing gravity in the strong field regime. And by the same token, because the exact form of the signal matched up with the prediction from Einstein's theory as to how black holes would produce gravitational waves, it provided arguably the most direct evidence to date that black holes exist and really do have their properties as predicted by general relativity. So if you put all that together, this was a big deal for fundamental science. So not quantum mechanics, but gravity. It's basically giving us greatly increased confidence that our theory of gravity is a good one. Next slide, please. But there's a second part to this. It was also a big deal for astrophysics. And the phrase that we often wrote when we were writing grant applications to do this sort of work was, we will open a new window on the universe. And then when we made the detection, we said, we have opened a new window on the universe. The point is this, that, okay, great, we've tested Einstein's theory of relativity, but we've done more than that. We've actually seen a pair of black holes. We can start doing astrophysics. We can say something about, well, how did this binary form in the first place? What were the normal stars that collapsed and led to this? And as I'll show in a moment, we've seen quite a few things now, and we can start doing statistics and working out the distribution of masses of stars earlier in the universe. So the point is, whereas we've done astronomy just using light, well, for thousands of years, arguably, we can now do astronomy with the gravitational field itself. So it's a new way of doing astronomy. So that was the second sort of fundamental new thing that this gave us. Next slide, please. And this was reflected in the award back in 2017, so very soon after that first detection of the Nobel Prize, to three of the pioneers of the field. So Ray Weiss on the left was one of the people that was one of the first to advocate doing building laser interferometers to do this. Barry Barish led the LIGO experiment for many years. And Kip Thorne is a theorist. He was actually, I think, was he executive producer, something like that, on the film Interstellar? You may know him from that. But anyway, he's a very well-known theoretical physicist, and he did a lot of the calculations back in 60s and 70s that helped lay the groundwork for really understanding the properties of black holes and how they can produce gravitational waves. So yeah, so that was the Nobel Prize. So let's move on to the next slide. So the story has developed since then. This is actually an animation. So can we play it, please? So what has happened since? Well, this is the single most exciting thing. We've seen a gravitational wave signal from a pair of stars that we think aren't black holes. We think they're neutron stars. This is an animation of it. And what basically happens is when they collided, they created a big explosion, because neutron stars are basically balls of matter. And so what you're seeing here is a lot of heat and light being produced as these two fluid balls crash into one another. And what that means is that as well as producing gravitational waves, there should be an electromagnetic signature to this sort of thing. So what you can see on this plot, the trace that's developing at the bottom, that is the gravitational wave signal, and the actual picture itself is how the fluid that makes up this system is behaving. So can we go to the next slide? So on the last slide, I used the phrase multi-messenger astronomy. What I mean by that is that for the first time, we were able to see something happen through the gravitational waves, because we detected gravitational waves from this event, but we also detected an electromagnetic signal. And what this plot here is showing is, so at the very bottom, you can see like a blue background with a little curve on it. So time is running along the horizontal axis. Frequency is running along the vertical axis, and the color is showing the strength of a gravitational wave signal. This track that bends upwards and then disappears, it's one of these signals, just like the black hole one, that starts off at low frequency and weak. Its frequency then increases and its amplitude increases, and then it disappears. So that's the gravitational wave signal. And you can see that at time t equals 0, it terminates. So that would be when the two stars presumably collided to form one. If you look at the top few plots, these are plots from gamma ray satellites. So not gravitational waves now, we're talking about electromagnetic astronomy. And there's quite a pronounced peak, I think it's about 1.7 seconds or so after the gravitational wave coalescence. This is a gamma ray burst. People had been detecting bursts of gamma rays for decades. One of the leading theories, but one which had never been confirmed, was that they were due to precisely this, to two neutron stars in spiraling and colliding. So this was sort of tying everything together. It was confirming this theory that gamma ray bursts were consequences of two neutron stars getting closer together and colliding. So can we go to the next slide, please? And in fact, what happened was, not only did the gamma ray satellites see this gamma ray burst, but slowly and surely, astronomers from all the way up and down the electromagnetic spectrum saw something. And that's what this plot shows. So it was seen in the gamma rays, as I've said, it was seen in X-rays, it was seen in the ultraviolet, it was seen in optical, it was seen in radio. If you look at those images at the bottom, some of those have got little crosshairs on them, and in some of those crosshairs you can see a little dot, and in some you can't. What's happened is that in those images where you can't see a little dot at the crosshairs, that was the image taken at some point before this event. Then just afterwards, there's a little dot there. There was a bright glowing spot that suddenly appeared in the sky that pinned down exactly where in the sky this had happened. So this was studied in unprecedented detail. A large fraction of all the big telescopes in the world, prompted by this, swung around and started looking at this precise point in the sky, and they built up a very nice picture of just what was happening and how the system evolved as time went by and how it got brighter and then it got dimmer again. So this really is multi-messenger astronomy. It's gravitational waves and traditional astronomy all the way up and down the electromagnetic spectrum coming together to give us a really detailed picture of this binary neutron star coalescence. Next slide, please. So the fact that we saw this event in both gravitational waves and electromagnetic waves allows you to do all sorts of interesting things. I'm just going to mention them briefly here. One of the things we could do was say a little bit about the matter, the material that made up the neutron stars. Basically, we could see how stiff it was. Because if the matter is really stiff, then the neutron stars would sort of be really big, whereas if the matter is really soft and compressible, they'd be small. And it turns out that shows up in some way in the gravitational wave signal, and we're able to show that these stars weren't too stiff. We're able to get a measurement of the Hubble constant, which is just some number that measures how rapidly the universe is expanding from this. The actual gravitational wave signal and gamma ray signal arrived within about 1.7 seconds of each other. According to Einstein's theory, gravitational waves and electromagnetic waves travel at the same speed. So the fact that those two signals arrived at almost the same time is consistent with that. We weren't expecting them to arrive at exactly the same time because it takes a while to launch the jet that we think produces the gamma ray. But basically we're able to show that the speed of gravity and the speed of light truly are the same to within about 1 over 1 followed by 15 zeros, so 10 to the minus 15, so very good accuracy. And then this last thing, so this relates to the picture. And for some reason, this is the part of the story that the media picked up on most. It seems likely that a lot of heavy elements, so things low down in the periodic table, were produced in this event. In fact, this is now a leading candidate for the production of heavy elements in the universe. A lot of gold was surely produced in this event, and some person worked out, I don't know, like an Earth's mass of gold or something was produced in half a second. We can't mine it, so it's no use to us. But anyway, lots of heavy elements like gold were produced here, and as I say, the media really liked that. So the point is, by seeing the gravitational wave signal and the electromagnetic signal, we're able to conclude all sorts of interesting things. So that's what the use of multi-messenger astronomy. Next slide, please. So we've actually now seen about 90 binary and spirals, so lots and lots, and they're displayed on this plot here. What's going on here is all the blue dots are black holes. What we've mainly seen are pairs of black holes coalescing to form one bigger black hole. The way this plot works is it's lots of vertical lines. There's like two lower blue dots. Those are the two original stars, and they coalesce to form one heavier star. So that's the top blue dot. If you look at the bottom of this plot, there are some orange dots. These orange dots are the things that we think are neutron stars, not black holes. So we've now seen two neutron star coalescences. The second one, unfortunately, we didn't see any light signal, so we couldn't play all the fun games with it. And we've also seen a few things that we think are coalescences between one neutron star and a black hole. So we kind of got the set now: black hole, neutron star, and neutron star. And we've got about 90 in total. So it's enough now that we can start doing statistics, which is nice. Next slide, please. So what's coming next? What's on the horizon? Well, let's see. So next slide. We were hoping to have more and better detectors. The detectors are being improved all the time. We've still got the two LIGO detectors that you can see in America. Um, there's a very good detector called Virgo in Italy near Pisa. There's a small experimental one, sort of a testbed geo. Kagra, I'm sorry, so that Kagra is now operational. So this slide is slightly out of date. There's a detector called Kagra in Japan that has recently become operational, although it's not nearly as sensitive as the LIGO or Virgo ones yet. And there are plans to put another big detector in India as well. So the more detectors you have, the better, because you can detect weaker signals and you can figure out what direction in the sky they're coming from much more easily. Because there's the directional information comes in large part from a triangulation timing effect. So having a whole network makes that easier. Next slide, please. The other big thing on the horizon are very ambitious plans to put a gravitational wave detector in space. This is the so-called LISA experiment. So LISA is an acronym too. It's Laser Interferometer Space Antenna. The idea here is that it's not quite an L shape. So the gravitational wave detectors on Earth were L shapes. It's like L shapes combined to form a triangle. So it's a triangular detector. So it consists of three satellites in a heliocentric orbit. It's orbiting around the sun, treading the Earth. And because it's in space, you can make it even bigger again. So the baseline, for the separation between these satellites is really big. I think the current idea is it should be 2.5 million kilometers, the separation there. So it's a really big detector, and we're hoping that it will be launched around 2037. And this will give us complementary information to the ground-based detectors because it will probe lower frequencies, which in practice means we'll see more massive, so heavier black holes with it. So we'll see different things with this detector. Next slide, please. But hopefully, we will make some new and different sorts of detections. As I showed you that slide early on, where I said there were sort of four broad classes of things we'd like to detect. Well, we've only seen compact binary coalescences so far. We've only seen the top left from that picture. So we hope that we'll soon see different, the other sorts of sources. But whenever anyone has looked at the universe in a completely new way before, there generally have been some surprises. So next and final slide, please. So we very much hope that there'll be something totally unexpected coming out of this as well. So that's it, everybody. That was my final slide. I very much hope that you enjoyed that and found it interesting. I wasn't able to keep track of the chat now, so let me take a look, and I'll be very happy to answer the questions that we've got there. So let me take a look. So there is a question here from, I think it's Nair. So here's the question. How can we prove that these waves are traveling with the speed of light? Okay, that's a very good question there. So I think there are two components to this. So first of all, if we just look at, say, the first detection we made, the binary black hole one, we used Einstein's theory to compute what the waveform would look like. And basically we got a sensible answer that matched up with what we observed. So in that calculation, there wasn't we did assume Einstein's theory, and hardwired into that is the idea that gravitational waves travel at the speed of light. But we didn't sort of, in that calculation, really allow that speed to be a free parameter and test for it. So what's probably more persuasive and more relevant to your question is what I said about the multi-messenger astronomy. So as I say, there was a time delay of only 1.7 seconds between us seeing the gravitational wave signal from that binary neutron star coalescence and us seeing the gamma ray burst. And if you divide 1.7 seconds by the time it takes light to travel the 40 megaparsecs that the source was from us, you find that ratio is about 10 to the minus 15. So the fact that those were so similar is a strong, it's not 100% rigorous, but it's a strong argument that those two speeds really are the same to about 1 part in 10 to the 15. So that's 1 followed by 15 zeros. Now, the reason it's not 100% rigorous is that no one knows for sure what the actual time delay would be between the two stars colliding and all of the complicated, mucky physics to do with the way in which the fluids collide and heat up, producing the gamma ray burst. But it's ballpark 1.7 seconds is plausible. So there's not a lot of room for any significant difference between those two speeds. And if they'd say differed by 1 part in 10 to the 12, then we would have seen a very big difference of like tens of minutes. I can't do the numbers in my head, but a much longer time delay between those two things. So that's relevant. Then one other component to this, one thing that we can do quite robustly and quite rigorously, even if we just see, say, a gravitational wave signal from black holes, is that we can look for so-called dispersion. So dispersion is the idea that if you've got a signal, some sort of wave signal propagating, that signal might be composed of different frequencies, some high frequencies and some low frequencies. Dispersion is the idea that the high frequencies and the low frequencies propagate at different speeds. What we've been able to do, just with our gravitational wave data, is look for dispersion and see if there's any sign of the signal getting distorted, like getting stretched out with the, say, high frequencies arriving too soon compared with the low. And we've seen no sign of that. So there's no sign of dispersion, which would be a dependence on the wave speed on frequency either. So as far as we can tell, these speeds really are matching up in the way that they should. So I hope that answers your question there. So then there's a question from Ines. Is there a difference in measurement techniques between gravitational waves coming from compact objects and primordial gravitational waves? So the answer to that, Ines, is yes. So obviously we use exactly the same gravitational wave detectors, but the way in which we interrogate the data is different. So when you're looking for something like a compact binary coalescence, we're in the position that we know in advance what shape the signal should be. It's one of these chirps that starts off at low frequency increases and the amplitude increases, and then it dies away again. With the gravitational wave, a primordial gravitational wave, we think a primordial, so early universe signal, is going to be much more random, like the electromagnetic background. So the only meaningful way you can look for that is to take the outputs of two or more gravitational wave detectors and you look for correlations between them. So the idea there is that if there's some like random seismic noise, say in the Hanford detector over here, and then there's some completely uncorrelated noise in the Livingston detector, because when a truck goes past one detector, there isn't a truck going past the other, those seismic noises won't be correlated, whereas the true primordial gravitational wave signal would be correlated modulo the short light travel time between the two detectors, which you can account for. That there'll be a common coherent part of the signal. The part of the signal that's the same, and that would be the genuine gravitational wave background. So that's how we do it. We look and see if there's a common piece of the gravitational wave signal between our geographically separated detectors. I hope that answers your question, Ines. There's another question here from there. What is the difference between the change in length and the strain data? Yeah, so I didn't explain this in my talk, but I think some of my slides mentioned, and certainly the abstract represented strain data. So strain is what we call the fractional change in length of our detector. So if these were like the two ends of one of the arms of our detector, as the gravitational wave comes through, there was a change in length, and it was ballpark 10 to the minus 15 meters. The strain is that change in length divided by the total separation, which was 4 kilometers. So the strain is a dimensionless number that says what the fractional change in length is of your detector. So that strain for that first detection, that's the thing that was 10 to the minus 21. So 1 divided by 1 followed by 21 zeros. So strain is how we more often talk about these things, because it's got nothing to do with the particular length our detector happens to be. So if someone else, so like the Virgo detector has got arms that are 3 kilometers long, not 4 kilometers, so that they'll get a correspondingly slightly smaller length change by a factor of 3/4 compared with LIGO, but their the strain that they would measure, the fractional length change they would measure, would be the same. So it's a more sort of robust measure of what's going on. So thank you for that. Now, then there's a question here from someone. I won't be able to read out the name because I think it's in a script that I can't read. But about Lisa, if you set 4 three-dimensional points, can you detect gravitational waves from all directions? All right, so that's a bit of a technical question. So the way in which you did get directionality comes from having multiple detectors. So 3 detectors is enough to get good directional information. But hang on, but let me just think about that question. So about Lisa, if you set 4 three-dimensional points, can you detect gravitational waves? So with regard to Lisa is basically 2 interferometers. It's like you can think of the triangle as one L shape and another L shape, and we happen to give them an arm in common. So Lisa will get somewhat less directional information than the ground-based detectors, because there are more ground-based detectors. Lisa's basically 2 independent detectors, but the story is actually a little more complicated than that, because some of the signals that Lisa will see will last quite a long time. And what do I mean by that? Like a significant fraction of a year. So what happens is Lisa orbits the sun, and in fact, as Lisa orbits the sun, it also spins around. There'll be Doppler shifts of the signal. So when Lisa's sort of moving towards the source, the signal will be blue shifted or increased in frequency a bit. And when Lisa's moving away from the source, the signal's decreased in frequency or red shifted a bit. And the way in which that Doppler shifting occurs itself encodes some directional information. And so Lisa will get directional information from that as well. So I hope that goes some way to answering your question. And then another question from there. So observationally, it is proved that gravitational waves are traveling at the speed of light, but how are they predicted to be equal? So I'm going to interpret that as saying why we made that prediction in the first place. Well, basically, it comes out of Einstein's theory of general relativity, which is a theory of gravity. So you might wonder why on earth, why does the speed of light appear at all in Einstein's theory of general relativity? Why does it care about the speed of light? What's that to do with gravity? Well, Einstein's starting point for his theory of general relativity was in fact his theory of special relativity. So you can think of special relativity basically tells you how to think about space and time when there aren't any gravitational fields. Excuse me. So it tells you how people measure distances, how people measure lengths, and how people measure speeds. And in Einstein's theory of special relativity, the speed of light plays a very important role. And one of the reasons it does that is that we've got this theory called electromagnetism, or Maxwell's theory of electromagnetism, that says how light should work. And Einstein wanted to make sure that everyone would agree on how light works, even if they're in motion relative to one another. So if I'm doing some experiments to do with light, say, and you're moving past me in some spaceship at half the speed of light, and you're looking at my experiments, Einstein wanted to make sure that we both got consistent answers. And the way he did that was sort of tinkering profoundly with space and time, but in a way that depended upon or made use of the notion of the speed of light. So in Einstein's special theory of relativity, everyone measures the same speed of light, even when they're in relative motion. Now, to come up with this general theory of relativity that has got gravity fields in it, Einstein's basic physical assumption was that if you just look at a tiny little bit of the universe, or some small laboratory, then things should look like special relativity. So if you confine your experiments to small laboratories, small volumes, special relativity still applies. And that's where, in a sense, where the speed of light enters into gravity, because locally you can sort of forget about gravity and just um, do experiments in a small laboratory, and then you should get the standard results of special relativity, where the speed of light does play an important role. So now I hope that answers your question. So I'm just looking at the chat and I can't see any further questions. Okay, so I think perhaps it's time to draw to a close in that case. So I'm very happy to do that. I hope you've all enjoyed it. I certainly enjoyed talking to you, and I've enjoyed the questions, so thank you very much for asking those. So it's time to wrap up. I don't know if we've got any end-out slides that we should be putting up now, but let me just remind you again that this is just one of a series of talks in this SOTSEF. Before I go, let me say we'd very much like to know what you think of this. There's a scannable QR code there, and there's also a web address. So if you could, ideally right now, leave us any feedback on what you thought of this, we would be very grateful for that. As I say, this is just the first of a number of sort of live talks and all sorts of things going on. So I very much hope that you'll be able to attend some of the other things as part of the Southampton Science and Engineering Festival. Quite soon this afternoon at 4 o'clock GMT, my colleague Sunny is going to talk about special relativity, so Einstein's theory of space and time that came before his gravity. So I'd very much recommend you to take a look at that. I can't think of anything else I need to be saying right now. So with that, I'll thank you all again, and I'll say goodbye. Bye-bye, everybody.